For the relevance for the lattice Gaussian free field.
Thank you, Atal, for the presentation, and I would like also to thank the organizer for this very nice conference. Okay, the subject of my talk will be basically surface interacting with an inhomogeneous interface. Okay, so the picture is not maybe self-speaking, but okay, you have a fixed crossable interface, which is my green plane or hyperplane, and I have a surface which can take different spatial configuration, and I will choose to put a term of interaction. I will choose to add some interaction term when the surface touch my my interface, and I will choose that interaction to be inhomogeneous in the sense that it will depend on the point of contact. And what I want to know is, okay, what is the effect of adding this energy interaction, and in particular, what is the effect of the inhomogeneity in the energy of interaction. So for this reason, I will just consider a very simple model for surfaces, and to me, a surface, it will just be the graph of a function say from the lattice to R. Okay, and I want the most tractable model because I don't want to have any trouble in studying this, because what I'm really interested in is the effect of the interaction. So what I will choose is the discrete Gaussian, my function to be the discrete Gaussian free field, or the lattice Gaussian free field. So let me recall or introduce the definition. So if gamma is a finite box included in Zen-Z, the lattice free field on gamma is defined as follows. With so I first defined the boundary of gamma to be the set of points which have neighbors that are not in gamma. Okay. And I will define my free field to be equal to 0 on the boundary, and the density of phi restricted to the inside of the box is given by P gamma d phi. It's equal to, so you have a normalizing term, which I call the partition function, and density is the sum over all edges in gamma of the square of the difference of phi. Okay, and this is the density with respect to the product, to the Lebesgue measure. So this is how I write it. So another way to describe the field is just to say that, okay, I have boundary condition 0, and the law of phi x given phi y, y given phi in the rest of the box, it is just a Gaussian of mean which is the arithmetic mean of phi among the neighbors, and of variance 1/2. Okay, so it's the simplest field, which is a basic Gaussian field, which is invariant by translation, which has 0 mean, and which satisfies the spatial Markov property, basically. Okay, so now let me tell you what kind of gift measure I want to consider on my surfaces. So I will have to introduce the disorders, or the inhomogeneity in the interaction. So I will consider omega x a fixed realization of a field of IID random variables. So you can think of it as a field of IID standard centered Gaussians. But we can be a bit more general, but I will assume for convenience that they are centered of unit variance. So this is just a matter of renormalizing, and I want my variables to have a finite exponential moment. So lambda beta is the log Laplace of my variables, and I assume that it's finite for all beta. Okay, I also give myself a parameter beta, which is the inverse temperature, and some h in R, and I define, so if Pn is equal to the measure of the free field on the box gamma n, where gamma n is 0 n to the d, I define the modified version of Pn, which is Pn beta h omega. It's absolutely continuous with respect to Pn. Okay, and the Radon-Nikodym derivative is given by 1 over Zn beta h omega. So it's a partition function which is there to have expectation 1. And then you have an exponential term which is given by the sum over all x in my box of beta omega x minus lambda beta plus h multiplied by the indicator function of phi x in minus 1, 1. And okay, and Zn is just the expected value with respect to Pn of this exponential thing. Okay, just to have a mean one. So, okay, let me comment a bit this expression. So, Okay, what you want is to have interaction only in the interface. So here, the interface is just ZD I want some thickness for my interface. So the interface of interaction will be given by ZD times the segment minus 1, 1. So I want to have interaction when the field lies in the interval minus 1, 1. The parameter h is somehow the mean of the interaction. Beta omega is there to represent the fluctuations around the mean. Okay, so when beta is large, basically you have somehow more disorder because you have more fluctuation around the mean. And okay, this lambda beta is just there for renormalizing purpose. I mean, we'll see its use, but basically it's not really important. Okay, and what we are interested in is you consider a large n, you draw some phi according to this measure, and what you want to know is whether your phi will have typically lots of contact with the interface or very few contact. Okay, so you want to understand in particular if h varies, we want to understand a transition between a delocalized phase with, say, a number of contacts which is little o of the volume of the box, and a localized phase with of order n to the d contacts. Okay, is everything clear? So, okay, I mean, it's kind of natural to see that when h will increase, somehow the contacts are more favored, so the phi will tend to localize more. And by point of contact, I mean the number of x for which phi x is in this interval. So the natural quantity to study, like for many models of statistical mechanics, is the free energy, which is given by f beta h, which is the limit when n goes to infinity of 1 over nd log Zn beta h omega. So of course, I mean, some work is needed to show that this exists, but the reason why it exists is basically because of superadditivity issues. Okay, when you sum over different boxes, you have some things that are independent, but you have to care about what occurs on the boundary, so it's not really superadditive, but okay, some people did this work. It's a result by Loren Koki and Piotr Milosz from 2010. Okay, so the limit exists and does not depend on omega, and you can also rewrite it as the limit of the expected value of the same thing. Okay. So why is this a relevant quantity to study? So this is something that is not too complicated to see. So let's take the derivative of log Zn with respect to h and see what we obtain. If you differentiate log Zn, so you obtain the derivative of Zn over Zn. And when you differentiate Zn, what happens is that okay, the number of contacts will naturally come down out of the exponential. So, sum over the x in gamma n of index phi x in minus 1, 1 times the exponential factor over Zn. And this is just the expected value of the number of contacts in your box. Okay, so in particular, if you divide by 1 over, if you divide by nd and you take the limit, what you obtain is that the derivative of f beta h is equal to the limit when n goes to infinity of 1 over nd times the expected value of this sum. Okay. Okay, so here I've interchanged derivative and limits, but the free energy is a concave function, so somehow I'm allowed to do that as soon as this derivative exists. And therefore, I mean, the derivative of the free energy with respect to h give me the asymptotic contact fraction. Okay, the asymptotic fraction of points which are contact points in expected value. So therefore, what we can deduce is that if this derivative is positive, then we are localized on the interface. Whereas if it's equal to 0, we are delocalized.
Is it clear that it's the same limit for every omega?
Yes. Yes, it's part of this result. But it's basically because the things are self-averaging. Because it looks like a sum of independent random variables. So now, let us try to look at what happened when you have no disorder. Okay, to try to understand the phase diagram of the non-disordered model, and then try to figure out what are the consequences of the introduction of disorder in the model. Okay, so first, I will consider very briefly the case where you have no disorder and in fact no interaction. So just give you some remarks about the behavior of the Gaussian free field. So, okay, by its definition, it's a Gaussian process. And if you look at the covariance function, so for the process defined in the box gamma n, it is given by the expectation of the integral from 0 to tau delta gamma n of So the covariance function is given by the green function on the lattice, and the green function evaluated at xy. It is the expected occupation time of site y for a simple random walk starting from x and killed when it hits the boundary of the box. So in particular, if you look at the variance at a point for some x which is in the middle of the box, it goes to infinity for d equal 1 and 2. So d equal 1, it goes to infinity like n, and for d equal 2, the variance diverges like log n. Okay, and when d is larger than 3, the variance is uniformly bounded. Okay, so somehow it will have some effect on the behavior, on the phase transition of our process. So let's see what happens now when h is not equal to 0. So in fact it was studied by Volthausen and Velenik in 2001. And among the things they prove, they prove things about the phase transition. So what you have is that you have a phase transition that occurs at 0. And if you look at the behavior of fh at the right of 0, it behaves like h squared for d equal 1. Like h over square root of log h for d equal 2. Okay, and like h for d equal 3. So let me briefly kind of justify the fact why the transition occurs at 0. So of course, if you look at z and h, the partition function of the system, of the pure system, it is smaller than 1 when h is negative. Okay, so the free energy is of course. So to prove that the free energy is 0, you just have to get some lower bound on it. Okay, the reason why it's smaller than 1 is just that it's the exponential of something which is negative. And if you want to get a lower bound, you can say that z and h, it is larger than, okay, so you have some contact that you cannot avoid due to my definitions. All the boundary points, they are contact points. So you have to take them into account. But apart from that, I can imagine a strategy where I have no contact in the inside of the box, and this gives me a lower bound for the partition function. So this lower bound is that z and h is larger than this times the probability that for all x in gamma n minus its boundary, phi x is, say, larger than 1. Okay, so I can... and to prove that the free energy is 0, I just need to show that the probability to lie entirely above the interface does not decay exponentially with the volume. Okay, and well, somehow it's quite natural to say that it shouldn't do that, because Okay, so in dimension 1, I won't try to give you a justification. In dimension 2 and more, in order to show that this does not decay too fast, you can say that, okay, with some probability which is proportional to the volume of the boundary, in the strategy you want to do, you want to apply, is to say that you want your field to be very high at distance 1 from the boundary. So let's say that you want to force phi to be larger than log n at distance 1 from the boundary. And so this costs you something like exponential c nd to the -1 times log n square. Okay, because well, log n square is just the term you get in your Hamiltonian, and you get n to the d-1 edges in which you have to n for this condition. And then conditionally to that, okay, what's inside will tend to stay high and not to touch the box back, just because the variance of the field, okay, is smaller than log n anyway. So it will not want to. Okay, so this kind of justifies that the free energy is 0. And as for the critical behavior, at least for d larger than 3, it is quite trivial to see that, okay, log z and h, by Jensen's inequality, it is larger than h times the expected value over the free field measure of the number of contacts. And because the variance of phi is bounded, okay, and because the phi's are centered, this is proportional to nd. So this gives you this lower bound for free. Okay, so well, until now we kept things quite simple. So let's see now what will be what happens when we add disorder into the game. So, okay, what we want to evaluate is the expected value of log Zn beta h omega. And there is a trivial way to get an upper bound on it, is by using Jensen inequality, and this is smaller than the logarithm of the expected value of z. Okay, and well, this quantity is just the partition function of the annealed system, the system where you average over the environment. And now, if you try to compute this, because of the definition of our Hamiltonian, it gives you something very simple. So when I compute the expected value of the partition function, I can use Fubini to interchange the two expectations. And then when I take the expectation of the exponential of my Hamiltonian, what the term with omega, when I take the expectation, I will get the log Laplace, and it will cancel with this. And then only h will remain. So that this is just equal to Zn(h), the partition function of the pure system. Okay, and this is this was the reason for my convention of putting the lambda beta here. And okay, so just give me this, and for this reason, what I have is that for all beta, f beta h, it is smaller than the free energy of the system without disorder, okay, which I called f of h earlier on this board. Okay, so there is another convexity relation which I won't detail, but it's not very complicated, that gives you a lower bound. Basically, it tells you that well, the free energy of this system, it is larger than the free energy of the system when you just cancel the omega without cancelling this term. Basically means that, well, in the interaction, you get at least the reward of, well, you get at least the mean reward, which is quite intuitive, in fact. So, just by this inequality, you are sure that you have a phase transition in H when beta is fixed. Okay. What I mean by that is the free energy is positive, and if you look at where the well, it's non-negative, and there is a transition between 0 and positive values which occur at hc beta, and hc beta is somewhere between 0 and lambda beta. So now the question is, okay, how much did I lose when I did this Jensen inequality? So basically what I say here is that, well, this inequality would be sharp only if Zn behaves more or less typically like its expectation. So a first way to ask the question is, okay. Is the critical point equal to 0? Okay, so do I lose something on the local, on the position on the phase transition when I do this, when I use the Jensen inequality? And okay, second thing would be, do we have the same asymptotic behavior when h tends to 0? So in the case where we have the same critical point, okay, do we also have the same critical behavior? Okay, I could also ask, do we have equality here? But in fact, okay, it's not a very, well, it's not very likely to happen. So, and in fact, I mean, it will never be true. So, but okay, these two questions are relevant. So, by adding disorder, do we modify the location of the critical point, and do we modify the characteristics of the phase transition? So, in the physics literature, the problem was mostly considered in dimension 1, okay, not really for, in the Gaussian case, but in the case of the simple random walk, which is maybe more natural in dimension 1. And so there was a paper by Forgax, Luck, Nguyen-Huizen, and Orland, appearing in 86. And okay, they had very convincing heuristics about the problem, and they say that at least when beta is small, so when the amplitude of the disorder is not too large, one should have HC beta, which is equal to 0. Okay, so this is for d equal 1. So 6 years later, there was another paper by Derrida, Hakim, and Van Imenius. And they had quite convincing heuristics as well. And what they said is that for all beta, HC beta should be positive. Okay, and basically afterwards, there was no real consensus in the physics literature about which one was the true one. So I mean, you could find a paper in favor of both directions, and in fact, the answer to the problem only came long after that, because when basically what was needed was a true mathematical proof, and there was a strong. I mean, both. If you look at heuristics, you could really believe the two, and it was in a joint work with Giambattista and Fabio Toninelli, where we proved that Derrida, Hakim, and Van Imenius were in fact right. And okay, the reason for the disagreement, in fact, was that HC beta is positive, but it's really small when beta gets small. So if you look at the asymptotic behavior of this guy when beta goes to 0, it is given by this limit. So the basically HC of beta behaves like exponential minus beta to the minus 2 times pi over 2, in some sense. Okay, and quite remarkably, this was part of the paper of Derrida, Hakim, and Van Imenius, and we confirmed the prediction in a paper which appeared this year, on the archive this year with Quentin Berger. But okay, somehow the case d equal 1 is a bit singular with respect to what happened in a higher dimension. So our work with Giambattista was to say what in our work with Giambattista we're caring about the higher dimensional case to see if something different happens. And we obtained the following result. So, 1, okay. For every, so the result is valid only in dimension 3, in dimension larger than 3. And first thing we proved is that for every temperature, okay, we have that the critical point is not moved by the introduction of disorder, but what happens is that okay, if you take Gaussian environment, and it should not be specific to Gaussian environment, you can say that the critical behavior is changed in the sense that instead of being of first order, the transition becomes of second order. So for the pure model in dimension larger than 3, you have a discontinuity around the critical point for the density of contact. And this discontinuity vanishes when you add disorder, even a very small amount. And in fact, the growth of the free energy becomes quadratic instead of linear around the critical point. Okay, and here, in fact, the upper bound is valid for any environment, but for omega general, we were only able to show that okay, so here I should that around the phase transition, okay, you have a polynomial lower bound, but the bound we have is quite bad. Okay, so this minus 65D has not any particular meaning, but well, first we couldn't get down to the 2, and second we couldn't get something which is dimension 3. Okay, so the workshop is about planar structure, so maybe I should say something about the dimension 2 case. So in dimension 2, our result is quite frustrating, in fact. So it's valid only when omega is Gaussian. And what we could prove is that, okay, if there is a shift of the critical point, it has to be smaller than beta to the 3 plus epsilon, okay, for beta small. Meaning that, okay, if you look at lambda beta, because of my assumption, it's of order beta square. So the trivial bound we had before was that hc beta was smaller than beta square. What we obtain is that, okay, this bound is anyway far out, and that if you look at the beta square scale, okay, hc is close to 0. But however, what we think now and I would say that well, I think that the critical point should, we think that the critical point should actually be 0 in that case as well. So I would be ready to bet something on that. More sloppy conjecture is to say that in dimension 2, in fact, the transition phase is the phase transition is smoother somehow than quadratic. Okay, so that okay, we have some strong heuristics to support that. This is a bit more sloppy, but well, maybe this has chances to be true. But it gives some kind of incentive to try to study the two-dimensional case. Okay, so in the remaining time, what I will try to do is to explain what are the ideas behind this this result. Okay, so in fact, one of the two bounds is really simple. It's the proof is 3 lines, so I will be able to show it to you. And then, if I have enough time, I will try to show the ID for why the converse holds. Okay, so. So I will stick to omega Gaussian, but I mean, you will see in the proof that it's just a restriction to make it easier to write, but it's by no means a technical restriction, and you can adapt the proof for general environment. And what we have is that for all beta, for all h, and for all d, f beta h is smaller than h squared over beta squared. Okay, so for free, okay, you get that, okay, provided that you are able to show that 0 is the critical point, which is in fact the difficult part, you know that the transition will be smoother than linear. Okay, and so how does the proof work? So the first thing we want to do, okay, so we have to evaluate the expectation of a log. It's not very convenient. So we transform it. We transform the problem into evaluating the expectation of a square root. By using just Jensen inequality. Okay. So just by using Jensen inequality, or I mean, you can instead of getting well, if you do this little trick before, instead of getting the annual bound, you get a bound which is slightly better when the expectation of the square root appears. And now, what we want to do to estimate this, okay, we want to show that the expectation of the square root is much smaller on the exponential scale than the square root of the expectation. So if this is true, it's because there is a very small event for omega that kind of carries all the expectation of Zn. So what we want to do is to make some kind of change of measure that will penalize this exceptional event. So I will introduce a new probability measure on omega. Okay, and I won't, for now, I won't specify who it is. So I have Gn omega, which is the probability density. So it's just a positive function which has expectation 1. And what I can say is that the expected value of square root of Zn, which is equal, in fact, to the expected value of square root of Zn Gn times Gn to the minus 1/2. By using the Cauchy-Schwarz inequality, I can say that this is smaller than the expected value of Gn omega Zn omega times the expected value of Gn omega to the minus 1. Okay? And this thing, okay, I can interpret it as the expected value of Zn under another probability measure, which is just the one defined by so basically, I mean, instead of applying Jensen to get an upper bound on the expectation of the square root, what I can do is, in the same process, I can change the probability measure, but I have some cost to pay, which is this thing. Okay, and now what I have to we have to find some clever change of measure that will give us a benefit here, which is much better than the cost we have to pay here. Okay, so naive but reasonable choice for our change of measure will be to change the means of our Gaussians. Okay, so instead of having centered Gaussians, we want Gaussians which have mean minus delta. So this corresponds to Gn omega, which is equal to exponential delta sum over x in the box of omega x minus delta square over 2, and maybe I have to put a minus here. Okay, so that, okay, and in fact, if I can really define this change of measure in any case. I don't need omega to be Gaussian to do it. But in the Gaussian case, the cost of the change of measure will be exponential delta square times the size of the box. Okay. So this is the cost. Now let's look at the benefit. So what I have done really is that I've replaced beta omega by beta omega minus delta beta. Okay, so when I take the averaging here, beta h omega, what I will get is not Zn h, but Zn h minus beta delta. Okay, so if I put everything together, just this, and my equalities, what I get is that the expectation of log Zn beta h omega, it is smaller than exponential delta square times gamma of n times delta square gamma of n plus log of Zn h minus beta delta, which gives me, when I pass to the limit, f beta h is smaller than delta square plus f h minus delta beta. Okay, and the delta is arbitrary, so I can optimize over delta. So in particular, if you think about it, if you take delta very small, it already gives you the fact that the annealed inequality that I had before is strict for every value of beta and h. And if you choose to take delta equal h over beta, okay, you get the result of our proposition. Okay, here you get f of 0, which is 0. Okay, so I mean, it's quite simple, and in fact, if you use Hölder instead of Cauchy-Schwarz, you can get a factor 2. But, so what's quite surprising is that here I've basically done almost nothing, and apparently when the dimension is equal to 3, this is sharp. So, I mean, do I have any time left?
Yeah, you have 5 more minutes.
Okay, so during the 5 last minutes, I will try to explain at least why it has chances to be sharp. So, what I will do is I will change my model for some kind of toy model, which at first sight it will seem completely unrelated to the model, but well, I will need you to trust me for 2 minutes. Instead of considering that my points of contact are given by this, I will choose to replace them by IID Bernoullis. And I will fix the parameter to be h times exponential beta square minus 1. Okay, and we are interested in small h. So P, we want to be close to the annealed phase transition, so P will be small. Okay, and let's compute the partition function, well, the free energy, which corresponds to this system. Okay, so I don't know, I will call it Zn beta h omega. And if you look at this, well, it is just basically n to the d, a product, well, Zn is just a product of n to the d replicas of the system of one element, okay? Because here you have IID Bernoulli, so everything factorizes. So this is just the expected value of log of 1 plus p exponential beta omega minus lambda beta, but I'm in the Gaussian case, so I can write things in this manner, plus h, and I have to put minus 1. Okay, so do you agree with this? Okay, I mean basically you will have the product over all x, but they are all the same. So okay, so now p is small. So what we have is that okay, we can write this as a log of 1 plus p psi, where psi is this random variable, and this is roughly equal to p psi minus p psi square over 2. Okay, so if I take the expectation, I get p times the expectation of psi minus p times the expectation of psi square over 2. And I hope that I can neglect the other terms, but in fact, if you do the computation, you will see that you can indeed neglect the other terms. So now the expectation of psi, it's exponential h minus 1, so it's basically h. And if you look at the expectation of psi square, if you look at the expectation of psi square, well, h is close to 0, so you can neglect it in that case. And it's just the variance of this guy, which is equal to exponential beta square minus 1. Okay, so if I replace p by its value, okay, and if my computations, I mean, if I've not lost anything in the Taylor expansion, what I have is that this is roughly h square over exponential beta square minus 1. So somehow, and I have a 2 here. So I mean, morally, it's almost the thing I had before. So I have a toy model for which the free energy is somehow and for which what I've done here is sharp. Okay, but you can tell me, okay, it has nothing to do with your model. First, the contact fraction of your model is small, whereas under Pn, the contact the probability of this guy of this is something which is does not depend on h. And the second thing is in the Gaussian field you have a power tape dependence, so you're far from being IID. Okay, so the first objection, it's easily to rule out because you can say, okay, maybe under the original measure the density is not small, but there is a simple way to change the density. It's just if you change the boundary condition. So instead of having boundary condition 0, I will have boundary condition UH, where UH is chosen such that the probability that phi x in UH plus 1, UH minus 1 is equal to the right thing. Okay. And by changing the boundary condition, I won't change the free energy. And the reason is if, in fact, in order to change the boundary, it's kind of equivalent to changing things that happen at distance 1 from the boundary. And the cost will be proportional to the size of the boundary, so you won't see it in the free energy. Okay, so I won't say anything about the fact that you have correlation. And sorry for the overtime. Thank you.
Quick question. Okay, let's thank Hubert again.